we're going to discuss strain gauge rosettes. And so we're going to discuss maybe right at the beginning, just a brief background, brief refresher. What is stress and strain? How do we measure strain? And then we'll go into what a strain gauge rosette is, why would we use them? And finally, we'll talk about some of the quantities that we can calculate using a strain gauge rosette. So the principal strains, the principal stresses, there'll be a few more parameters. And then at the very end, also talk about critical plane analysis and fatigue life analysis and how that's useful and why we might use it. So to get started, we'll just give a brief background on the basics here. So what is stress and strain? Stress is defined as a force divided by area. So I've got a cylinder here. I'm applying a compressive load, and the stress experienced by this cylinder is this force divided by the cross-sectional area of the cylinder. So stress is kind of like the internal forces that are resisting the applied load here. Stress is expressed in units of pressure, so pascals, MPa, or in English units, PSI or KSI. And with stress, there's kind of two different knobs that we can turn to reduce the stress experienced by a part. So we can either increase the area over which our force is acting on, or we can reduce this force. Conversely, if we were to, let's say, reduce the effective cross-sectional area, so if my part had a little notch cut out in it like this area of lower cross-sectional area is kind of now the effective area over which my load is applied, and I will see a higher level of stress in this specimen. And you might, see a notched specimen like this in a tensile testing machine, for example. They put notches in the test specimen in order to control the location at which that specimen will fracture. Strain is a change in length over length. So if I've got my same cylinder and I'm applying a tensile load to it, this cylinder will actually deform and its length will change. So this outline here is the original length of the cylinder, and now that I've applied this load, I've increased the length of this specimen by delta L, so the change in length here. The strain is this delta L divided by the original length of the cylinder. So basically, it's the amount that the device under test deformed. Strain is kind of funny because it is a dimensionless quantity. It's a change in length. So let's just say meters divided by meters. So it's unitless. However, for most materials, because the strain or the change in length is so small when we apply a load, we typically multiply this strain by 10 to the 6th, and we express this unit in microstrain. Strain is positive, so positive delta L. If there's a tensile strain, so something pulling this material apart, and it's negative, we call that compressive strain. So if this force was reversed, and we were compressing the cylinder, we would have a negative change in length, and that would be a compressive strain. Stress and strain can be related to each other by Hooke's law. So we've got Hooke's law shown here. It states that the stress is equal to the modulus of elasticity times the strains. And this Hooke's law holds true in this linear region of the stress-strain curve. So the slope of this line is E, the modulus of elasticity. After a certain amount of stress is applied to the part, this relationship no longer holds true, and we call this point the yield strength. And after the yield strength, the relationship between stress and strain is nonlinear. And so we see kind of a curved line here. We eventually get to the ultimate tensile strength of the material. Afterwards, the specimen begins to fail. So as the strain increases, we see the stress lower until we fracture the material. And so this Young's modulus is very important because typically we're not able to measure stress directly. We need to measure strain and then try and relate that strain to the stress using rules like this one. So let's talk about that then, since we can't, or it's very difficult to directly measure stress. Let's talk about how we determine how much stress an object is experiencing. And we do that by measuring strain. So we measure strain using something called a strain gauge. So a strain gauge is a long resistive wire that we've kind of folded back on itself, embedded in a very thin foil. So this is an image of a strain gauge here. We see we've got some wire that's kind of bending back in on itself. And then we've defined some of maybe the terms that you might see associated with the strain gauge. So we've got this area here, the measurement grid, the active length of the gauge, and the transverse length. Now, as the strain gauge, let's say we install it on a test article, as the part deforms, the strain gauge will also deform, and that causes a change in resistance of the gauge as this wire is either pulled apart or compressed. Now, that change in resistance can be related to the strain by a quantity known as the gauge factor. So the gauge factor of the strain gauge is equal to the change in resistance of the gauge divided by the nominal resistance divided by the strain. So using this relationship, we can identify when this changes or has a certain change in resistance, we can identify the amount of strain that caused that change in resistance. Now, there are a couple of important items to note with strain gauges. One is that when we put a strain gauge at a location on our device under test, we are measuring the average strain over this measurement grid area. So if you have a test object that has very high strain gradients, and what I mean by that is the strain varies very rapidly at different locations along the test part, it's important to use a small strain gauge, because if you were to use a bigger strain gauge with a higher surface area like this, you are kind of averaging the strain over the entire grid area. The drawback of that is with a strain gauge with a smaller grid area, there is less surface area through which to dissipate heat. Strain gauges with shorter grid areas are worse at dissipating heat, and that can affect your strain measurement. Two other important concepts to discuss, and they're very important to today's webinar, strain gauge rosettes, is the active length of the gauge. So a strain gauge is really a uniaxial sensor. When I place this on a device under test, I am measuring the strain in this direction. I'm not measuring the strain perpendicular to the gauge or at a particular angle to the gauge. This strain gauge only measures the strain along the active length of the gauge. So if you're taking a measurement with a single strain gauge, you kind of have to already know the strain field on your test object, so you can align the strain gauge with your strain field. Now, this isn't very convenient. I think there are many cases where we're unsure of what the strain field on the test object is, or perhaps there's both a strain acting in, for example, this direction and a strain acting in this direction. In which case, we are not measuring all of the strain on the test article, and we'll need another method in order to correctly measure the strain. Now, when we're measuring strain, we install this strain gauge in something called a Wheatstone bridge. So Wheatstone bridge is basically just a voltage divider. We have a number of resistors in this circuit, and we are able to relate the output voltage, so the voltage measured across points 1 and points 2, to the voltage that we supply the circuit. And so when we're measuring with strain gauges, we simply replace one or multiple of these resistors with our strain gauge. If we replace one resistor with the strain gauge, we have a quarter bridge strain gauge circuit. If we replace two of them, we have a half bridge strain gauge circuit. And if we replace all four of these resistors with strain gauges, we have a full bridge strain gauge. And we can relate the output over the supply voltage. We can calculate that that's equal to the gauge factor of the strain gauge times the number of gauges in the bridge times the measured strain. So we can basically, by measuring the output voltage, calculate the strain at that point on the structure. These are some examples of real strain gauges. So you can see there's a thin substrate that's placed on the material, then the gauge is bonded to that substrate in this picture. And in this picture, you can kind of see the very, very thin resistive wires. And then there's solder tabs for correctly wiring the gauge together. So like I mentioned previously, the orientation of the strain gauge is really important in order to correctly measure the strains on a test object. So for example, if I have a cylinder like this and I orient my strain gauge so its active length is in the same direction as the applied load, I will correctly measure the full compressive strain that this test object is experiencing. If I misalign my gauge, so in this case, we've completely misaligned the gauge with the applied force, we will not measure the compressive strain. There might be, some strain measured due to Poisson effects and due to the transverse sensitivity of the strain gauge, but we will be missing this compressive load. And so, instead of measuring with the single strain gauge, we can use something called a strain gauge rosette. A strain gauge rosette is typically three-wire quarter bridge strain gauges that we place in a particular orientation. The two most common ones being what you might call a rectangular orientation, so gauge 1, gauge 2, gauge 3, or a kind of like a T orientation here. And what these strain gauge rosettes allow us to do is basically by measuring the strains and doing some math, we can determine the maximum principal strains that the device under test is experiencing at that point. We can determine the maximum shear strains, and we can also then use that information to calculate basically a strain history versus time of any kind of angular orientation of our gauge. So the rosette strain gauge allows us to determine essentially the entire strain field at the point at which the rosette is placed. So it kind of solves that problem of us not knowing the orientation of our strain field. So it's important to use a rosette if you do not have a uniaxial strain field, or if you don't know the direction of the strains in your test object, because if you don't use a rosette, you might measure a lower strain value than what the device under test is actually experiencing. If you're looking to do multi-axial fatigue analysis, then it's a good idea to use a strain gauge rosette, because the strain gauge rosette allows us to basically calculate strain time histories at multiple different angles or orientations at our point, and we can use those different strain time histories and we can do fatigue life calculations, and we can determine in what direction our part experiences the most strain or the most fatigue. And it can also be very helpful for correlating to simulation. Oftentimes simulation engineers will basically run a simulation on their part. They'll calculate things like the von Mises stresses, they'll calculate the principal stresses and so on. And these are all things that we can calculate using a strain gauge rosette and directly compare with the simulation model. So like I mentioned before, there's several different types of rosettes. There's T rosettes, so this is just two strain gauges, one at 0 degrees and the other at 90 degrees relative to the other gauge. These are only used when the principal strain directions are known in advance from other considerations, so they're often used on things like pressure vessels and shafts and torsion, because we already, based on the loading conditions of those items, have an idea of the principal strain directions. In other cases, we use either a rectangular rosette, so a 0.4590 strain gauge rosette, or a delta rosette, a 0.60-120 rosette. There's not much difference between using a rectangular or a delta rosette. Historically, rectangular rosettes were a little more common because the reduction math is a little easier. So converting these strains to basically the strain tensor and then to the principal stresses and strains. The math is a little easier with the rectangular rosette than it is with the delta rosette. But now with modern computers, we just have the computer do all the math for us. So there's practically little difference today between which gauge type you might use. Maybe a more important decision is whether you're using a planar rosette or a stacked rosette. So these gauges can either kind of occupy their own individual space on the device under test, or we can stack them on top of each other. And there's benefits and drawbacks to both cases. So the big advantage of a planar array is that it has superior heat dissipation to the test part, simply because there's more area over which we are dissipating any heat that's generated inside the gauge. The big maybe drawback of a planar gauge is if we are testing an object that has large strain gradients, so from maybe point to point, the difference in the strain value is very high. Because with a planar rosette, we're doing basically the exact same thing that we were seeing with just a single strain gauge, where we are essentially calculating the average strain over the kind of the area occupied by this strain gauge rosette. So if the strain is very rapidly changing through your test object, then we might not get an accurate result with this planar setup. A stacked rosette is, for that reason, very useful when there's large strain gradients in the part because the kind of effective measurement area is much smaller, but a gauge is much worse at dissipating heat. So the self-heating on this gauge will be much more highly. So if you're using a stacked rosette, you might need to use a lower excitation voltage into the gauge to avoid overheating the gauge and potentially burning out the strain gauge. So with a strain gauge rosette, we can determine the planar strain field that our device under test is experiencing at that particular point, at the point where the strain gauge is installed. Now this strain field or this strain tensor is commonly seen in simulation. We have two normal strains, so epsilon x and epsilon y. You can also kind of see it on this image here where we've got epsilon x in this direction, epsilon y in this direction. And then we also have two shear strains, epsilon xy, and it's the same value here, epsilon xy. And so when someone running a simulation model is doing a durability analysis, they can essentially generate this strain tensor at every single element on their model. And from this strain tensor, we can calculate a number of different quantities. The ones that you may be most familiar with are, for example, two principal strains and the angle of that principal strain. And so this strain tensor is kind of a building block. After, if we've been able to calculate this tensor, we can calculate a whole bunch of different durability related quantities that are really useful in helping us design a structure. And so we'll talk a little bit about how we can determine this strain tensor from a strain gauge rosette. A few other items that we can calculate, focusing on a rectangular strain gauge rosette. These can also be calculated from a delta rosette. We've got the tensor elements, so the normal strains, the shear strains. We can calculate our principal strains and our principal stresses. We can calculate the angle of our principal strains. We can calculate things like the biaxiality ratio, which gives us some information about the state of stress or strain that our test object is experiencing. And then things like the von Mises stresses and strains, the Tresca stresses and strains, and some critical plane math. So we can have many outputs from a strain gauge rosette. They really give us a ton of useful information about what is happening to our test object at the gauge location. So just a quick illustration of what rosette data might look like. I have a 0, 45, 90 rectangular rosette here. So this is the 0-degree channel, this is the 45-degree channel, and this is the 90-degree channel. And something where I've been asked this question before and there's been general confusion is if you were to do a durability type calculation in, let's say, Nastran or something like that, you might see a single value plotted for, let's say, the principal stresses and strains or the von Mises stresses and strains. But when we perform a physical test, we have a strain versus time history, and we do the calculations done for each point in time. And so the rosette quantities are constantly changing based on the values of the 0, 45, and 90 strain time histories at that moment in time. So instead of having a von Mises stress, or I'll say a principal stress at a single value in a single angle, those time traces may be changing in time, or those values are changing in time depending on the values coming from my strain gauge rosette. I've got a strain gauge rosette shown here on the right-hand side. I've got basically gauge 1 or gauge A, gauge 2 or gauge B, gauge 3 or gauge C. And from these strain gauges, I can write these three equations. I can write an equation for the strain measured at epsilon A, an equation for the strain measured at epsilon B, and an equation for the strain measured at epsilon C. So I have three equations and three unknowns, epsilon X, epsilon Y, and gamma XY, so the shear strain. And using this information, I can solve for these three quantities, and I have my full strain tensor. And as a note, epsilon XY is equal to half of gamma XY. From there, we can easily calculate the principal strains. So I've got three equations here for epsilon 1, epsilon 2, and epsilon 3, which is often used when you're calculating the von Mises stresses. These equations are nice, but I find it to be a little more instructive to show how these quantities are calculated using Moore's circle, because Moore's circle gives you some nice kind of graphical insight as to what's really happening at maybe different angle directions on our strain element. So we're going to run through an example where instead of using those equations that we showed on the previous page, we calculate the principal strains using Moore's circle. So I've got a rectangular rosette, and let's just say I have some single value calculations or single value strain numbers. So gauge 1 has a strain of -800 microstrain, gauge 2 measured a value of 0 microstrain, gauge 3 measured a value of 400 microstrain. I can convert these values to my stress tensor, so I'm just doing that quickly here, and I get, and I should say my strain tensor, and I get a strain tensor with the values where D11 or epsilon X is -800, D22 or epsilon Y is 400, and D12 is 200. And so we can use these values and we can calculate the principal strains using Moore's circle. So we're going to go ahead and do that. I've got my strain tensor shown here, and we're going to kind of walk through step by step what we would need to do to determine the principal strains. So I'm going to plot my data in this display here. Note that the x-axis is the normal strain and the y-axis is my shear strain. So my gamma xy divided by 2. And also note that typically the sign convention is such that we draw this axis as positive downwards. So these values here are positive shear strain. The first step to generating Moore's circle would be to plot my epsilon x and my gamma xy over 2, and then my epsilon y and my negative gamma xy over 2. Based on my strain tensor, I have these 2 points here. We'll go ahead and plot them on this display, and I get something that looks like this. My next step would be to calculate the average strain, or the center point of Moore's circle, which I can do by just taking the average of these two different points. I do that here, and I get a value of -200 microstrain. And so I'll draw that point here on my display. And from here, I can calculate the diameter and the radius of Moore's circle. So we'll calculate that now. You can calculate the diameter using this equation here, the radius, and I get a value of 632 microstrain for the radius, or double that for the diameter. And so using this information, I can fully draw Moore's circle. And what Moore's circle is doing here is it is for my point on my test structure, it is describing the relationship between the normal strains, so my epsilon x and my epsilon y, and the shear strain at a specific or specified angle. So this circle here is kind of giving me all of the possible stress states at that point, depending on my angle. And graphically, I can see a couple of nice things here in Moore's circle as well. One of them being that at the point of my maximum normal strain, my shear strain on my part is 0. And so these points here, this point here and this point here, my points of maximum normal strain, are the principal strains, and they're very easy to calculate now that we have all of these different points. I basically just need the radius of my circle, and I can easily calculate principal strain 1 and principal strain 2. So these are these values shown here. From our rosette, from our initial rosette, if we go back here with just these values, we were able to relatively easily calculate the principal strains at that location on the test object. We can now convert those principal strains to stresses using a couple of different material parameters. So one that we discussed earlier is Young's modulus, which is the modulus of elasticity. The Young's modulus is the ratio of the stress along an axis divided by the strain in the range of stress in which Hooke's law holds, so in the linear region of the material. And Young's modulus is typically very large. So for steel, it's about 200 gigapascals, for aluminum in the neighborhood of 69 gigapascals. And one thing that it's very important to be careful of is when you're performing calculations like this is be very cognizant of the units that are used. It's very easy to have a mismatching units between, let's say, gigapascals and megapascals, and then your answer might be off by a factor of 1,000. We also need to know the shear modulus of our material. So the shear modulus is essentially the Young's modulus, except instead of relating a normal stress to a normal strain, it relates a shear stress to a shear strain. And the shear modulus is defined as the shear stress divided by the shear strain. So likewise, this needs to occur in kind of the linear region of the material in order to be valid. And then we also need to use Poisson's ratio. So when we apply a load to a 2D material or a material in multiple directions, we deform the material in the direction of the applied load. So you can see this green square has gotten much longer. But when it's elongated in this region here, that also means that the material has to undergo some deformation in this case, the Y direction and the Z direction as well, which causes some additional stresses in the material, which we need to take into account. And we do this by using Poisson's ratio, which is the negative ratio of the transverse to the axial strain. So it basically tells us how much the material will deform in this direction, given the deformation in this direction. Once we know any two of these material properties, it's very easy to calculate the third. So for example, the shear modulus is just equal to the modulus of elasticity divided by 2 times 1 plus Poisson's ratio, and we can write equations like this for our other properties. So if we know E and Poisson ratio, we can calculate the shear modulus, for example. We can then go from our strains to our stresses by applying Hooke's law. For a 1D loading case, it's very simple. We just have sigma equals the Young's modulus times epsilon. For a 2D load case, it's a little more complex. we have sigma x, sigma y, and the shear stress. And we need to make sure we include the effects due to the deformation in our other axes. So we've got this term here, this Poisson's ratio times the strain in the y direction. Once we know those parameters, we can kind of easily calculate our principal stresses from our principal strains. So I've got principal strains listed here. To calculate principal stress 1 and principal stress 2, I can just apply these equations here, and I get my principal stresses. I can calculate, again, many other items from a strain gauge rosette. So one item that it's easy to calculate after knowing the principal stresses is the von Mises stress, which is sometimes called the equivalent stress or maximum distortion energy. So the equation for the von Mises stress is shown here. So I can see I've got my principal stresses 1 and 2. And then basically I subtract the 2, square them, and then add the 2 squared, take the square root of that value. And the von Mises stress is often used as a yield criterion for multi-axial loading. And so if I have a part, I might calculate the von Mises stress at multiple locations, and I might compare that to the yield strength of the material. If my von Mises stress is below the yield strength, I feel somewhat confident that I've designed the part such that it won't go plastic. This is also a really nice way of reducing our stress or strain tensor. In this case, it would be the stress tensor to a single number value. And we often use the von Mises stresses to visualize the stress field on an object in a simulation. I'll also make a note is that the von Mises stress is usually greater than our maximum principal stress. So in the case that we calculated before, the von Mises stress would be 178 megapascals, whereas our max principal stress was below that value. We can also calculate something called the biaxiality ratio, which is the ratio of the smallest calculated principal stress to the largest calculated principal stress. It's a number between -1 and 1 and gives us an indicator of what kind of stress or strain field we have in our part. So if we calculated a biaxiality ratio of 0, our part would be in uniaxial tension or compression. If it's equal to -1, it's pure shear. And then if it's equal to 1, it's equibiaxial. And we can use this information along with the angle of our principal stress to determine, do we have a uniaxial, a proportional, or a multi-axial loading condition. So for a uniaxial strain field, our ratio is about 0 and our principal angle is nearly constant if we were to plot it versus time. For a proportional strain field, the biaxiality ratio and our angle are nearly constant, but the ratio does not equal 0. And for non-proportional loading conditions, the ratio and the principal angle are varying with time. And this is essentially our multi-axial loading condition, or indicates a multi-axial loading condition. There's a number of other quantities that we can calculate from rosette. So we talked about von Mises stresses and strains. We can calculate the stress or strain at a specified angle. We can calculate the absolute minimum principal, absolute maximum and the absolute minimum principal stress and strain to get an idea of the maximum normal stress felt by the device under test at a certain point. And then we can calculate things like the von Mises stresses and strains and the signed von Mises stresses or strains, which is something that we need to do if we want to use our von Mises stresses and strains for fatigue life calculation. We basically assign a direction to our von Mises stress, either positive or negative, based on the maximum principal stresses. And once we do that, we're able to do fatigue calculations with our von Mises stresses. This generating a stress or strain curve at a specified angle is really interesting. And that's what we'll talk about in this next section where we talk about using information from a strain gauge rosette to perform fatigue life calculations. And so I have, let's say a couple of gauges placed on this particular part, and this part is going or experiencing multi-axial loading conditions. So it's experiencing normal stresses in two different directions, and maybe it's experiencing some shear as well. Based on the loading conditions here, it can be a bit of a challenge to determine how to perform a fatigue life analysis. Because we don't know what the direction of maximum strain or of our kind of maximum amplitude load cycles is occurring. And so we can use this relationship here to generate strain time histories at various different angles at the location of our strain gauge rosette. And then we can cycle count all of those different strain results in order to determine at which angle our part experiences the most damage, or where we calculate the maximum damage. And we call this the critical plane approach. So basically what we're doing is we're generating multiple different time histories at set angle increments. So in the example that I'll be showing, we basically generate a strain versus time history at 0 degrees, 10 degrees, 20 degrees, and so on. And then we cycle count all of those time histories, and we calculate the amount of damage that occurred at that specific angle. And that gives us a lot of information as to, in what direction do we need to design our part to withstand the loads that are being put into the test structure. So what is kind of the critical direction, and are we going to see fatigue failure based on the damage calculations that we perform? Some conclusions based on what we've discussed so far is that if you do not know the strain field of your test object, it would be a good idea to use a strain gauge rosette. Rosettes do have some drawbacks. You need more channels. So instead of a single channel for a strain gauge, you need 3 channels for your 3/4 bridge strain gauges, which may increase maybe some instrumentation effort, but they give us quite a bit of useful information when trying to analyze whether a part will fail, or when we're trying to correlate a simulation model. So again, item number 2 here, with the rosette, we can basically compare our strain tensor that we calculate to the CAE stress tensor. We can calculate a number of very commonly used CAE metrics for evaluating the durability of a test object. And we can use a rosette to determine the type of loading that our device under test is experiencing. Okay, that's all I had today. Thank you, everyone.